Okay, so what we've been talking about last time was different bases, and we talked a little bit about taking numbers that are written in these other bases and converting them into base 10. We also said, what does it mean to have a different base? And we need to really understand what a different base means when you talk about base 16. Because remember, with base 16, we actually had to invent, so to speak, new digits in order to deal with that. Okay. So, and remember that fundamentally, what is another base? The idea behind another base, if you look at this picture in the middle here, is that it just represents a different way of grouping. And that different grouping becomes translated as different place values. Instead of 1, 10, 100, you have what we think of as, for example, in base 5, you'd have 1, 5, 25, etc. Okay. So when you write down a number, if it's in a different base, then each digit represents something different. Okay. So we talked about converting in one direction. Now we're going to go the other way. The other way is slightly harder. The calculations aren't harder, but it's not as immediately intuitive. So, suppose we have the number 97. Let's convert that into base 5. And again, remember when we say the number 97, since there's nothing written next to it, that's just good old 97 base 10 that we are well familiar with. So how do we convert this into base 5? Well, the thing to remember is that a different base fundamentally means a different grouping strategy. So instead of when we have 97, we think of it as saying we have 9 10s and 7 1s. But if we're going to express this number in base 5, that's not what we're going to say. What we're going to say is, how many 1s does it have, how many 5s does it have, how many 25s does it have, how many 125s does it have, etc. All the values that are appropriate to base 5. So the question is, how do we start answering this question? Is the first thing we ask, how many 1s does it have? No, it doesn't make any sense. It's got 97 1s. It doesn't help.
What's the first digit?
Exactly. We start off by saying, what's the first digit? So where is the first digit going to be? Exactly. Because does it have any 625s? No. So you can put a 0 there or an X there just to remind yourself. Does it have any 125s? No. Does it have any 25s? Yes. Now how many 25s does it have? 3. Okay. Now that's sort of more immediately obvious because I made base 5 and base 10 and they kind of work together nicely. But how, in terms of calculations, how would you figure out that it has 3 25s? Division, exactly. How many times is 25 going to 97? All we're doing is division. So you can write out this little scratch calculation on the side. 97 divided by 25, and it's going to give you 3. But what else do we need to write down that's going to be important? The remainder. Exactly. And what's the remainder? It's 22. So we know it's got 3 25s. Now, how do we go about figuring out how many 5s are in there? Yeah. What we've got left over is 22. So that's the part that hasn't been put into groups yet, if you like. So that's the part we need to continue grouping off. So 22 divided by 5, and what's that? That's 4, remainder 2. So it's got 4 5s, and then what? And then we're just left with 1s, so clearly the remainder 2, that means there are 2 1s. Okay. So, how many 25s are there? There are 3 of them. How many 5s are there? There are 4 of them. And then there's just the final remainder, which tells you how many 1s there are. So, it's not necessary, but 2 divided by 1 equals 2. Just so you understand. Okay. So does that make sense? Alright. So how should we do converting 155 into base 4? Should we do it together, or you guys want to crack?
Let's try it. No, I want to do that.
Okay. All right. So you can race ahead, and I'll do it very slowly here. So what's the first thing we need to do? Right. So and what goes in the table? 5 for base 5, we run 525, etc. What are those called? He's calling the numbers on top, but they mean something. They represent something. Those are the place values. Yes. So for base 4, we need our place values. So what are our place values for base 4? 1, 4, 16. Right. And by the way, how do we always get our next place value? Times 4. Not squaring it, times 4. 64. And then what's the next one? Times 4. 256. Okay. Now do we have to find the next one, or can we stop? How come we know we can stop? Right. We don't have any 256s, so we know we can stop right there. So there's no 256s. Does it have any 64s in it? Yeah, at least one, right? It's bigger than 64. So 155 divided by 64 equals, and you got to figure that out. Okay. So it's going to be 2. Right. So then you need to figure out the remainder. Now in the previous one, we could more or less do it in our head. Maybe you can't figure out the remainder in your head. That's fine. 2 times 64 is 128. So what you need is 155 minus 128, and that's your remainder. And what is that? 27. Okay. So we know we have 2 64s. So what comes next? Okay, so what do we do? Yep. 27 is what remains, divided by 16, and what's that? That's 1. And then what do we need to do with that? Right. So we know it's a 1, so fill that in. Now you got to find the remainder. So the remainder, that's pretty easy. That's just 27 minus 1 times 16, which is 11. So what do we do next? 11 divided by 4. And that's just 2. Clearly the remainder is 3. Presumably y'all can do that in your head, I hope. And then you don't have to do it, but 3 divided by 1 equals 3. And then we're done. So, how many 64s? There were 2. How many 16s? There was 1. How many 4s? There were 2. And then how many 1s? There are 3. Okay. You dig? Okay, so does that make sense? Okay. So, come back to something that we mentioned last time. How does all this stuff apply for computer information? Let's just mention this a little bit. Computers run on electricity, and in electricity, the easiest thing to measure is on or off. In fact, we talked about that in a different context earlier with circuits. The easiest thing to measure with electricity is there a signal or isn't there a signal? So on or off. We're going to represent on and off with zeros and ones. So in a sense, with computers, the only thing you can really represent directly is zeros and ones. Well, what do we know about a system that contains only zeros and ones? What system is that the same as? That's base 2. So that is exactly, in effect, that's the system that computers work on. Computers work in base 2. And this is called machine language. Other names this goes by: binary data, bits, and machine language. So anytime you hear any of those things, those are just computer people talking about base 2. At least base 2 as computers use it. So how do computers use base 2? And how do they use these zeros and ones? Let's check it out. Okay. Well, first of all, let's go the easy way. Here is a number written in base 2, which is like machine language. So what number is this in our language, base 10? That's the way that it's written. But how do we convert this to base 10? What number is this in base 10? How do we figure this out? Okay. So we do have to set up place values. But which place values are we interested in? We're interested in base 2 place values. Because in what base is the number written? Right. So, and base, yeah. Actually, you'll always write down the place values for the for the odd base, because that's what that's the hard thing to figure out. So for base 2, we have 1 and then after 4 we have 8, and then we have 16. And how many of these do I need? 6, exactly. Because we've got a 6-digit number, so we've got to figure out what each of those digits are worth. So it's 1 1 0 0 1 0. So what is this number equal to? What does that first one represent? 32. What does the next one represent? And then there's some zeros, and what does the other one represent? 2. So how do you figure out what this number is worth? Add them up. Now base 2 is also easy because you don't really have to. You could multiply 1 by 32, but I think we know ahead of time what the answer is going to be. So this is just 32 plus 16 plus 2. So this is the number 50. So that's how a computer writes the number 50. Yeah. Right. So the computer has to go through all of that. But how is it that computers are actually able to get things done? Well, in the sense that how come we don't have to sit there all day while they multiply? Because this seems like it would take so long. Computers are very, very fast. They work quite literally at the speed of electrons. Electrons go quite fast. So sure, it seems like it's slightly inconvenient to have to work in base 2, but when you can do billions of computations per second, it goes a little faster. And that's the idea. Okay, great. How many 4s do we have in this number? Right. Okay, so now the other way around. So, for example, when you type in to a computer 45, computer's got to translate that into base 2 in order to work with it. So, let's help the computer out, because it needs our help. Okay. So to convert 45 to base 2, what do we have to do? Okay. Well, here's the we don't really need to make a table with the place values for base 10 because we know what the place values are. There's no mystery there. Like we're not going around wondering what does that 4 represent. So we make our table for base 2. So 1, 2, 4, 8, 16. How far do I have to go? When can I stop? 32, 64. Okay, how come right there? Right, because it doesn't have any 64s in it, so we know we can stop there. So now what? Yep. Yeah. So 45 divided by 32 equals 1, and then what else do we need? Remainder is 13. Okay. So straight off we have 132. Next, 16 divided by. Sorry? What is it that we have left over? 13. So what is it that we're trying to put into groups? No. What is the cluster that we're trying to put into groups? Right. And then so we have 45, and we've already picked off a group of 16. So what we have left is a group of 30 is not a group. What we have left is 13. So it's 13 divided by what? 16. Well, what's 13 divided by 16? 0. So there's nothing going on there. So what does that tell us that we have to do? Yeah. So how many 16s are in this number? None. So again, remember place value is really important. The number 205 is not the same as the number 25. Right? So that's why we have to put that 0 there for the 16. Because it shows us there are no 16s, and what's coming up next are 8s. Okay. So now what do we do? (13) divided by 8, which is 1, remainder 5. So we know we have an 8. 5 divided by 4 is 1, remainder 1. So we know we've got 1, 4. And what next? Yeah. And you can check that just by saying, or write it out I should say, by saying 1 divided by 2 equals 0, remainder 1. And then finally 1 divided by 1 equals 1. And we're done. So there were no 2s, and there was 1, 1. So there you go. When you type in the number 45 to a computer, it sees 101, 101. Oh, no, because what are we doing? What did we do in the first example, and what did we just do in this last example? It's written how, and we're converting it to what? Right. So remember that it's when you write it in base 2, the question you need to ask yourself is, what is each digit worth? That first one, what is it worth? It's not worth 100,000. To figure out what it's worth 32. And we're collecting everything that every digit is worth. The second one, completely different problem. We know what it's worth, but we need to group it differently. And grouping, if you like, is kind of the same as dividing. Base 10 is what we always use. Because what are the place values that we always use? Ones and then tens, hundreds, thousands. So this base 10. Sorry? Yes. Okay. So Tracy's question is a really good question because it reminds us that depending upon what direction you have to be mindful of which direction you're going in, because that tells you how to handle the problem. Do you have something written in a strange and unusual base and you have to put it in base 10, or is it the other way around? And that completely determines how you treat the number that you're given and how you approach it. Okay, so talk a little bit about numbers here. Next, what about text? So how does a computer handle letters? Let's see. So let's take the word cat. So in base 10, how would you represent the word cat as numbers? What would C be?
Oh, C would be 03.
Yeah. And what would A be?
01.
And what would T be?
0.
What letter of the alphabet is T? It's the 20th letter.
20.
So you write it as 20. And then how would you do this? So that's if you wanted to send the word cat in code. And then what about going the other way? What if you received a particular code and you had to decode it? Well, the code that you got would look like 030120. And you'd have to say, how do I decode this? So the first thing you'd have to do is break it up. Right? You wouldn't take the entire number and try to decode it. You know that you'd have to go in 2-digit chunks. So the first chunk would be 03. What's the third letter of the alphabet? C. Next chunk would be 01. What's the first letter? A. Next chunk would be 20. What's the 20th letter? T. So in that way you could decode this string of seemingly random numbers with this very important message. So why don't you guys convert this to letters using base 10? Okay, so how do you get the very special message? Okay. So yeah, go ahead. Okay. Yes. So what's the first thing you have to do there? Until you get to what? Okay, right. So the point I'm trying to make is that 0.805121215. The first thing you have to do is break it up in these chunks. So that, because you're not looking for the whatever 8 millionth or 80 millionth letter, right? First thing you're looking for the 8th letter, and the 8th letter is H. Next, you're looking for the 5th letter, which is E. Then you're looking for the 12th letter, which is L. Then the 12th letter, which is L. Then the 15th letter, which is O. So, hello. Okay. So I'm actually teaching you at this moment very simple encoding and decoding. So how do computers do this? So again, we've been using base 10. Computers, as we know, use base 2. So how do computers do it? Well, note first off that computers are not going to say the letter A gets the number 1, the letter B gets the number 2. Because guess what gets the number 1? The number 1 gets the number 1. So where do they start? Capital letters A through Z get 65 through 90. And then lowercase a through Z gets 97 through 122. And in terms of base 2, those are those numbers right there. So no, yeah. Yeah. This convention comes from early. I mean, this goes back to really like the early days of computer programming. Like off the top of my head, I would say the 60s, maybe even earlier. And so this way of encoding is called ASCII coding. It's ASCII stands for something which I forget. And at that point, they decided we need the numbers 1 through 64 for numbers, and then we can do letters. And it was just somebody just decided that, and now that's how it's done. And then there are also codes for things like periods and commas and all that stuff. And so you might wonder, why is the number 127 assigned to a period? Well, just because that's what someone did. 127, of course, in base 2. Okay. So, first of all, note this. Using this coding system, how many digits do you need to represent a letter? Not just a lot. How many digits? For computers. In base 2, how many digits are we using? 7. In base 2, 1000001. How many digits? 7 digits. So in base 10, we've got the letters go 1 through 26. In base 2, counting both lowercase and uppercase letters, they go 1000001 up through, well, with a little gap in between. Well, the uppercase letters go 1000001 up through 1011010. That's how we represent uppercase letters. Similarly for lowercase letters in base 2. So, let's convert capital C to binary code. So, there are 2 ways to do this. Let's do one way. One way using this system. So one way is to take the letter convert it to base 10, and then convert it to base 2. Now, again, using this system, what is, and again, I'm showing you this because this is actually how the computers do encoding. Again, this is called ASCII code. What base 10 number is the letter C? It's using this ASCII system. What is capital A? 65. So what is capital C? 67. Okay. So now that we know in base 10 it's supposed to be 67, we want to convert that to base 2. And how do we do that? Well, we know how to do that because we just did it. Yes. So, we're going to convert 67. So we go 1, 2, 4, 8, 16, 32, 64. It should be obvious that that's where we stop. So what do we have first? 164. Now after we have 164, what's left over? 3. So what digit comes next? How many 32s are there? How many 16s? How many 8s? How many 4s? So remember that 64 divided by, 7 divided by 64 equals 1, remainder 3. So we've got zeros for all those, and then how many 2s? In 3, how many 2s are there? And then how many 1s are there? 1. So there you go in base 2. In ASCII code. Okay. This is not the only way to figure out the answer though. There's another way. You might think it's harder or simpler, it depends. Just like we said, think about what happens in base 10. In base 10, you say capital A is 65, so capital C is 67. You can do the exact same thing in base 2, if you don't mind counting in base 2. So in base 2, what is capital A in this system? Yes. 1000001. So then we just have to count to B and then to C. So the question is, after 1000001, what's the next number? Right. 1000010. If you like, just looking at the end, the next number after 1 is 10. And then what's the next number after 10? 11. Of course, with the 1 in the front. So if you can just count 2 numbers, that will also give you the answer. 1000011. So of course you have to be, to do that, you have to be comfortable with counting in base 2, which is separate scale. You dig? Which part? The part about counting? No. What's the next number? And again, just looking at the end, right now we have 11. What's the next number after 11? 100. Because you want to add 1. But, so... Alright. So we're gonna do that in a second, but... If you have 1000011, what's the next? So actually, hold on. Let me do it like this. So for A, we have 1000001. So we know that for B, we have 1000010. What's the next number? Well, then that next number is easy. It's 1000011. Now what's the next number? Can't put a 2 in the last place, so you got to go to the next place. But you can't put a 2 in that place. So what happens to the 1 in the first column? This goes to 0. What happens to the 1 in the next column? It goes to 0. What happens in the next column? It goes to 1. The thing is, it's base 2. You've only got 0 and 1. So the next number after 1 is 0, but then you have to put something in the next column. So you're constantly going to the next column because it's only base 2. You only got 2 digits. There's no such thing as like 1, 2, 3, 4, 5, 6, 7. We don't have that. It's just 0, 1, and then go to the next column. So that's why sometimes counting in base 2 can seem like it's on fast forward because you're always going to the next column very quickly. You mean, are you asking what's the next number? Okay, well what's the next number? Where's the first place that we try to add a 1? Where's the place that we add a 1 to? Which column? The 1's column. Can we add a 1 in the last column? Sure. Now what's the next number? 10001. And what's the next digit? Well, when we try to add a 1 to this 1, what happens? This goes to 0, and then what happens in the next place? And that's going to be a 1, because it carries, if you like. It's constantly flipping. So sometimes it's easier to go from right to left. In fact, it's usually easier to go from right to left for this reason. Okay, so you've all seen the next problem already. So what we've got here, this really looks like computer code, machine language. So how do we convert this into a message? What do we what's the first thing that we have to do? Yeah, we have to break it up. And we know that in base 2, converting to letters, how big are the chunks that we need? Every 7 digits, exactly. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, and then like that. Okay. So, how do we convert these numbers? Alright. So, one way, so we're not going to do, like I said, there are 2 different methods. We're not going to do both methods for this problem because that would be twice the work. So I'm just going to pick one method and go with it. So because it's more consistent with what we've been doing so far, I'm going to use the first method, which involves converting the numbers between bases as opposed to counting. Okay. So first of all, let's go this other way. So we've got a number in base 2, so what's the first thing that we have to do? Convert it to base 10. Convert to base 10. then assign the correct letter. Okay, so let's take the first one, 1110010. So how do we convert that? Well, 64, 32, 16, 8, 4, 2, 1. So this is 111 0 0 1 0. So how do we convert this? Well, in base 10 we know it's got a 64, it's got a 32, it's got a 16, and it's got a 2. And then the question is, what is that? Well, add it up. 6, 8, that's 114. So now the question is, what letter is 114? So this actually requires a little bit of work, since in this system letters don't go 1 through 26. 114, first of all, is 114, is that going to be an uppercase letter or a lowercase letter? It's going to be a lowercase letter. So all we have to do is figure out which lowercase letter it's going to be. Alright. So I will give you a nice little shortcut to figure this out. Notice that 97 through 122, we can make that look like 1 through 26. How can we make that look like 1 through 26? How can we make, so we want to make 97 look like 1. How can we do that? You subtract 96. So if you just subtract 96, then whatever was 97 is now 1. 98 is now 2, etc., etc. So 114 minus 96 is 18. So what letter is 18? Is 18th? So that's R. Sorry, lowercase. R. Okay. Next. No, I'm going to need more room. Okay. So the next one we need to do was 64, 32, 16, 8, 4, 2, 1. This number, which was 1, 1, 0, 0, 0, 1, 1. So this is 64 plus 32 plus 2 plus 1, 6, 97, 98, 99. So this is 99. Okay. What did I mess up? It may not make sense.
Is this supposed to be in order? That's what I want to know.
Yeah, let's say it's in order. Okay. So, okay. So what letter is 99? And how do you know that directly? How can you see that? Yeah. Right. So there's a certain amount of counting here. If you know that 97 is A, 98 is B, 99 is C. Another way to say that is 99 minus 96 gives you 3, and what's the third letter? C. And then finally we'll do the last one. One, one, 0, 0, 0, 0, 1. Alright. Why don't you guys finish the last one? Oh, actually the last one is easy. Why is the last one easy? Right. Because this one's actually already written out. It's right over here. So there's nothing to figure out. You've already been told that this number is the same as A. So we already know this is so finally our code is RCA. So that requires a little bit of work, but it's not the most awful thing. Okay. So, let's see. Any question about how this works? Shaquille, any questions? No. Lance, any questions? Ashanti, any questions? No. Okay. Yes. Yeah, and certainly, of course, if I were to give you a message to convert, it wouldn't be one involving like 20 letters, because that doesn't test any skill. It would just, it tests a skill, but it would just take forever. All those ones, absolutely, absolutely. Yes.
How do you divide into 2 parts? All digits we divide into 2 parts.
Yes.
How do you do it?
How what?
How do you do it in 7 parts? You like put all the numbers, 0, 1, 0, 1. That is the number. We divide it into 2 parts, right?
How do you know they're supposed to be 7 digits long?
Yes.
Okay, how do you know they're supposed to be 7 digits long? Because what are our codes for letters? Look at the, and again, this is using this system, which is called ASCII. Using this system, that is what our letter codes look like. So how many digits do we need? We need 7 digits. Right. As opposed to base 10. In base 10, how many digits do we need? In base 10, how many digits do we need? We need 2 digits, 1 through 26. In this system, how many digits do we need? We need 7. So you know that you have to look at the first 7 digits, and then that's going to convert to a letter, etc., etc.